Okay, we're going to talk about waves in 3D, all right? And so you can imagine in this case, you might have a point source right here, and this might be air, and it might be sound, and that sound is going to travel out in 3 dimensions, okay? Now, clearly this isn't going to be a transverse wave. It's going to be a longitudinal wave, and it's going to have areas of high pressure and areas of low pressure. You might consider these to be what's the word? Compressions. Sorry, couldn't think of the word. Compressions. And these to be rarefactions. Okay. It's sometimes hard to wrap your head around what's happening with sound waves in air. They're often drawn as transverse waves, but that doesn't make a lot of sense, right? How can a transverse wave travel out in 3 dimensions? This illustrates it much better. You can imagine that the dark areas are high pressure and that the light areas are low pressure. And then you can also imagine how it is that your ear is able to pick up this sound. You have a membrane stretched over, your ear canal, and these pressure waves come and they cause it to oscillate back and forth. And then via like a complicated set of bones, which are connected to nerves. I mean, it's more complicated than this, but this is the basic gist of it. These vibrations are then interpreted by your brain as sound. So what we're interested in doing here is we want to know, as the energy, which is, essentially put into the system at the source. So this might be a speaker. This might be someone like snapping their fingers. That is the source of all the energy in the system. So you can then imagine, right, the full amount of energy is put into this, let's say, compression, but as it travels out, the amplitude is going to decrease. The amplitude of this wave is going to decrease due to the fact that the same amount of energy is now spread over a much larger surface. So we recently looked at how energy is proportional to the square of amplitude. That having to do with the velocity at which your oscillating mass is essentially crossing the center point. If you have double the amplitude, right, you then have double the restoring force. So if we were, say, talking about a mass on springs, okay, if you have a low amplitude, you have a low velocity as that object crosses the center point. If you have a much higher amplitude, right, if you stretch your springs much higher, if you have a much higher amplitude, well, the restoring force is proportionately larger. That's Hooke's law. And therefore, the velocity coming through center is going to be much higher, right? So if you double the amplitude, you double the velocity coming through here, and you know from kinetic energy that you then get a 1/2 mv squared relationship. So doubling velocity increases the energy by 4 times, tripling it by 9 times. Okay, so that's where this comes from. Okay, now we're going to introduce the concept of intensity. Okay, so intensity is going to apply to a situation like this where you have pressure waves moving outward from a center. Okay, and the definition of intensity is it's going to be power for area. Okay, so unit-wise, power is in watts, area is in meters squared. So you get I is equal to watts per square meter. So how many watts are striking a surface per square meter? Okay. So in this case, power, not in this case, in all cases, power is energy used or energy transferred every second, right? So it's energy over time. Okay. So the units here then are going to be joules per second per square meter. So how many joules per second per square meter are striking a surface? All right. And if you think about it, okay, if we talk about power, well, seeing as how the wave is, it's going to be moving at a velocity set by the medium. Okay? In other words, like at a certain temperature, all sound and air travels at like, let's say 331 meters per second. Okay. At a bit of a higher temperature, it might travel at, 340 meters per second. So it's temperature dependent. So on a certain day, right, the velocity that the waves are traveling at is set. So in other words, the amount of time that it takes for, say, a wave to take a certain amount of energy from point A to point B is going to be set at a certain temperature. Okay? So the time factor in here is essentially related to the velocity at which the waves are traveling. If that makes sense to you, if we say like double the amount of energy in the system, okay, it's going to still take the same amount of time to get that energy from point A to point B. So the time factor is going to be based on the velocity that the wave is traveling. Okay, so then in that sense, power here, since this is fixed, is going to be proportional to energy. Power is proportional to energy. Okay. At a certain point away then from a source, okay, and this is, now we're thinking in 3D here. Let's say we set up like a detector. Okay, and we'll call that R. And then we take that detector and we move that detector, oh, can't do that. We move that detector farther away. Regardless of how much energy we're pumping in here, it's going to take the same amount of time to get to the detector regardless of how much energy we're putting in, right? We're going to have bigger amplitudes traveling outward, like, we might have that, and then we might have this, okay? That's how that energy is going to manifest itself, but it's still going to take the same amount of time to get to this, say, like 1 meter squared detector. What we want to know is what is happening to the intensity when that wave arrives at, say, R, and then at 2R and 3R and so on. As it goes out from the center, what happens to the intensity? Well, it's going to drop, and you might already suspect that it drops at a squared distance, but we just want to prove that and make sure that that's true. So, again, intensity is this. It's power over area. Okay, it's power over area. We also saw that that energy and power are going to be proportional to each other if you keep time the same. So you can then also say this is true. If energy is proportional to the square of amplitude, what can we say about intensity in terms of the amplitude? What do you think? If we say these are proportional, then we would say this is also going to have to be true. Okay, so again, you can imagine that now what we're going to do is we're going to imagine a situation where we have a source, and we're going to try to imagine this shell, this expanding shell. Okay, so what is happening to the surface area of, say, this compression as this increases in distance out from the center? We might know that the area of a sphere is equal to 4 pi r squared, right? So the area of this shell is equal to 4 pi r squared, okay? So what we'll do here is we'll try to figure out what exactly we're talking about. So we're just going to take a slice of this. The source is meant to be right at the center, and we're going to imagine projecting outward from there like this. A little bit hard to draw, but we'll see if we can do our best. Doesn't look quite right to me. Let's fix this up. Okay. So let's say we pick a point on here. So we're picking a point off of that sphere. Okay. And we're going to say that this distance is r away from the source. Okay, so some distance r away from the source. What we want to do is we want to imagine a kind of like a slice of the surface of that sphere. Okay, and then we're going to imagine when we get to 2r, what's happened to that. Okay, so by the time we get to 2r, we're like this, okay? And we could call that like area, we just call it A. By the time we get to 2r, we've now got 4 times the area, okay? And we get to 3, you've now got 9 times the area, etc., right? So you can see there that the area is growing at a square to the distance away that we are, okay? And you can also see then that as you move away, all right, the energy is spread over a larger and larger area. And because of that, right, you have the same, if you want, energy, okay, but divided by a larger and larger value. So here you have etc. Okay, so we would say then that the energy drops off, or is proportional to 1 over the square, okay, of the distance away, or 1 over the radius, all right? So another way to say that is E is equal to 1, or not equal to, but proportional to D, 1 over D squared. This is a really kind of common occurrence in physics, right? The energy is spread over a larger and larger area because the area covered by the same amount of energy, right? This whole black spot never gets any more energy added to it. It just gets continually spread over a larger and larger and larger area, okay? So if that's true of energy and the waves are always traveling at the same speed, we can say the same thing for intensity. Intensity drops off at a squared distance, okay? And there we go.